Right. Yeah, thank you for being here in the lecture. Naririnig niyo ako? Sorry.
Yes po, sir. Good evening po.
Okay, good evening,
Yes, sir. Good
Julius.
evening.
Good evening din, Sam. All right, for today, we will be discussing the final, I think probably the final requirement for this module, the exercise 2.2, which is kinematic analysis. Right? Right. Why do we do kinematic analysis? The point of kinematic analysis is to determine, for example, if you are dealing with a rock slope, you would want to determine how this rock slope might actually fail. Okay? And when you're talking about rock slopes and failures, there are actually four main types of failures that you can encounter. You have your toppling, your planar, and your wedge failures. The fourth one is the circular failure, but circular failure is really more on soil mechanics, and that was already tackled in the previous module, right? Now, before we dive into the whole exercise, let me define some terms. One of which is the term for engineering geology when you're talking about let's see some point. When you're talking about bedding planes, joints, faults, foliations, and all the mechanical breaks in rock that reduce their strength significantly, we call them discontinuities. Okay? And we characterize discontinuities in terms of their geometry mainly, which includes their orientation, persistence, spacing, roughness, and infill. I think I have some illustrations here. Right. Orientation, we will define them in terms of azimuth and your dip angle, but we will be gonna go back to that later on. All right, let's first talk about persistence. You can see here, what you're seeing here are side view or cross-sectional view of, sorry, may ingay ba? Audio. Going back. Okay, we have a cross-section view of two rock slopes, A and B. Okay. And persistence, basically persistence is the length of the discontinuity relative to the outcrop. Okay. If this is the outcrop or the slope cut profile, we normally talk about persistence relative to the height of the outcrop or the slope. Okay. From now on, I'll be referring to the outcrop as the slope, rock slope, right? And these are the discontinuities. Okay. Now, persistence, normally, we will call a discontinuity as highly persistent if it is actually cutting or almost cutting through the whole slope, rock slope. Okay, like this J1 um, discontinuity. Okay. Or in other books or other standards, sometimes they use 3 meters as the lower limit for a highly persistent discontinuity. Okay. On the other hand, we have another rock slope here, and you can notice that the discontinuities are relatively short. Okay? And that's what we normally call as low persistence discontinuities. Now, in terms of stability, that first that will have implications on how the rock slope may fail. If you have even just one discontinuity that is highly persistent, it can easily create an unstable block that can cause a large failure, like in this illustration. On the other hand, if you have low persistence joints, what they would normally form are small blocks, and they can fail as small blocks. And we call that, in engineering geology, we call that phenomenon unraveling, okay? Or piece by piece failure or removal of rocks from your rock slope. All right. Now that's persistence. Other stuff that we use to characterize is continuities. You also have your spacing, roughness, and infill. Let's go back again to this illustration. Spacing is, in essence, it's the when you look at two parallel discontinuities, spacing is the distance between two parallel discontinuities of the same set. Okay, that's important to note. They have to be of the same set. And what set I'm talking about is basically joints that are parallel are or of the same origin. For example, if these are bedding planes, okay, we can consider them as one set. Okay, right? Again, spacing is about the distance between two parallel bedding planes. Okay. Sorry, two parallel discontinuities. Okay. All right. What's next? I think the next one is infill. Infill is basically the stuff that's inside your discontinuity. I think I already tackled that in the GSI lecture. Okay. Although you have to be very careful with dealing with infill. The infill of discontinuities normally, for example, for the Philippines, normally it would be clay or silt. Okay, due to the humid environment, we normally have a lot of clays everywhere. Although there are certain circumstances where you might encounter cementitious infills like quartz infill or calcite cement infill. And in this case, and yeah, I think this one is a good. This photo is a decent example of quartz or cementitious infill in discontinuities. You can see it. Sorry. Anyway, I just want to see this photo. Okay. Um, I think this one. This one. All right. You can see here, you can see in this photo, you have like a solid rock and you have like white lines. These are your quartz veins, or if you are an engineering geologist, these are quartz cement and just discontinuities. And they can actually strengthen the rock. Okay? Rocks with quartz or calcite cement in their discontinuities can be stronger than a rock without any discontinuities at all. Okay, let's go back to the document. Roughness is basically the physical roughness of the discontinuity surface. I think that was just tackled in the shear strength of discontinuities lecture and quiz in the previous weeks. Okay, so where are we? Yeah, so that's how we characterize discontinuities. Now let's talk about the types of rock failures. Okay. All right, this photo is, I think you can readily see that you have a relatively tall rock slope and you have a very prominent plane, okay, exposed plane. Okay. As a geologist, okay, you would normally see this bare or exposed rock as indicative of recent landslide or recent rock failure. Okay. And this is what we call a planar failure. Okay? You basically have one plane and that acts as the sliding surface of your rock slope. This second photo is, at least you can see here, at least you can see here, you have a relatively, a very polygonal surface of exposed rock. And you actually have at least one, two, and three discontinuity sets. Okay. And what happened here basically is that your these two discontinuities, they have actually intersected. Okay. And they basically sliced the rock into a big chunk of block that had undergone sliding in this direction. Okay. Now, what does this third discontinuity do? Okay. This third discontinuity essentially acted as a releasing discontinuity. So it released the rock block so that it can actually fail or move or slide out from the rock slope. And this is what we call the uh, releasing joint. Okay. Okay. All right. And now let's talk about the third type of rock failure, which is toppling. Okay, sorry, I don't have a photo, but toppling is basically you have one important, or probably at least one of the most important characteristics of toppling is that you have a relatively steep rock slope and you have discontinuities that are actually dipping opposite of the face of the rock slope, right? As you can see here, the rock slope is pointed this way. The face of the rock slope is dipping towards this way, while the major discontinuities here are actually dipping on the other direction, right? And once you have formed enough columns of rocks that are unstable, these blocks can eventually sort of collapse or tumble forward. Okay, hence the term toppling. Mhm. Now let's talk about orientations. Discontinuities, of course, are essentially defined by their orientations, especially when you're talking about kinematic analysis, on when you're trying to understand the relationships between the rock slope and the discontinuities themselves. Right. The first term that you have to understand is the term dip. Okay. This is just basically the inclination relative to the horizon. If this is the horizon and this is your let's say this is your discontinuity, you essentially just have to measure the angle between the face of the discontinuity and the horizon. Okay, and that's what we would call dip or dip angle. Okay, it's essentially the same as the dip that we refer to in your classic geology. The second one is the dip direction or dip azimuth. Okay? This one refers to the direction of the dip relative using azimuth format. Right? Actually, I have a nice illustration here. Okay, this is the dip. And right, we have here the plane of the discontinuity. Okay. And in classic geology, we normally first we use the strike and dip convention. Okay, I think that's what you still use in structural geology. I'm not sure. But if some of you would be familiar with the strike and dip notation, in which first we measure the direction of the strike and then measure the direction of the strike relative to the north, like north 50 east or north 50 west. And then we also express the direction of the dip direction, like north 50 west, north 50 west, northeast or southwest. Okay. Like this one. Okay. So in this example, you have your strike and dip notation. So you first measure the direction of the strike, and then you measure it relative to the north. This is 45. Then we can call this north, 45 east. And then you also have to add the dip direction, which is southeast dip. Okay. Now, if you're going to express this in the azimuth, dip azimuth notation, all you have to do is just measure the direction or determine the direction of the dip. Okay, extend it like that, and then measure it relative to the north in the bearing notation. Right? Hence, this is 135 azimuth. Okay. Now, for example, if you have another dip here, let's say let's say you have another bed here that's pointed this way. All you have to do again is to just determine the direction of the dip and then measure it relative to the north. Okay, so that's 90, 180, 270, and then I think this is probably like 20. Therefore, this is just azimuth 270 degrees. Okay, right? And this is what we use in engineering geology, and I think even in the mining industry, this is what they use. Okay, and this notation, I think has an advantage, especially in engineering, because for one, you're just using one. You just have to use a number to express the direction of the dip, and that would be easier to manipulate if you're using some software or some calculators as opposed to this North 45 East. Okay. And second, of course, once you get used to this system, it's easier to plot this this notation. Okay, it's more intuitive once you get used to it, right? Now, we will since we're doing kinematic analysis by definition is just it's just about the analysis of orientations. Okay. Kinematic analysis is not limited to the discipline of geology. In fact, if you're doing some radio engineering and signal engineering, like cell phone towers or radio towers, we actually also have to do kinematic analysis to basically determine like what direction would have the strongest signal or what location of the cell phone tower would give you the maximum amount of coverage and so on and so forth. Okay. And interestingly, communications and radio engineers also use a compass. I think it's a I think it's a sight-based compass. They just sort of have a monocular compass where you sight the distance and from there you can determine the dip angle and the azimuth of the location that you're trying to sight. Anyway, going back, since we're analyzing orientations, and from here, it's obvious that discontinuities, you have your dip angle, you have your azimuth. These are actually 3D features, and it would be more convenient to express them in a simpler graphic, like in a 2D representation. Okay, hence we use the stereographic projection. Okay, and yeah, what we're gonna use here is the lower half hemisphere of stereographic projection. And also note that there are two main ways to represent a plane or a feature in stereographic projection. One is to use planes or arcs, and the other one is to use points or poles. All right, I think I have to briefly review the stereographic projection. Right, to be honest, as a student, I did not understand how stereographic projection works. Like 2 years after graduating geology. Anyway, it's actually a very abstract concept, and it's better taught using more practical or everyday objects. Okay? This is a concept that I did not understand while listening to a chalkboard lecture. Anyway, to do this, imagine you're drinking or you have a bowl of ramen noodles. Okay? So this is your bowl, and this is your face. It's quite elongate. You're happy. These are your eyes. And what you can see is what? You can see the bottom of the bowl. Okay? And you're quite anxious. Right? So you can see the bottom of the bowl. And let's say this is your what you can see from the top view. Okay, hmm, all right. Now let's say this is north and this is the south direction. North, south, west, east. Okay. All right, let's say you have a plane. All right, let's say you have a plane here. Let's say you okay. So this out of the page is your west direction and into the page is your east direction. Okay. Now let's say you have a plane somewhere in here. Let's color it red. Let's say you have a plane that is you have this plane, okay, that is like cutting through your bowl. Okay. Okay. When you're doing stereographic projection, using the lower hemisphere, of course, you're only looking at the lower part of the bowl. Hence, you're trying to imagine how will this plane look if it's actually slicing or intersecting this bowl. Okay, you can see here that the intersection is sort of dipping like towards north. Okay, and it's sort of almost west east in strike. Okay, so this would actually look like this. Okay, okay. So this one, for example, let's say this is a let's express it in the dip direction dip. So let's say this is 0, 0, 0. That's the azimuth, meaning that's due north, and then the dip angle is 45. Okay, so that's how we write uh, dip direction and dip azimuth in engineering geology. All right, so the intersection of that discontinuity relative to this bowl would be something that's lunging towards north. Okay, and it's also gonna be somewhere halfway between this equator and this tip of the circle. Okay, because it's 45 degrees. Okay, now if let's say you have a discontinuity, let's say 0, 0, 0, 20 degrees. Okay, that would look something like this. Okay, that would be a much gentler plane. Okay, and it will basically intersect the bowl at a, of course, a gentler angle. Okay, and if you look at it from top view, the arc plot of that discontinuity would be closer to the northern edge. Okay? Okay. And then if you go further, let's say you have 0.00005. Okay? It will be an even much gentler plane. Okay? And it will probably be almost be touching the northern part or the northern edge of your steering net. Okay. Okay, so you just have to remember that arcs in stereographic projections, of course, their outermost tangents will always point towards the dip direction. So that's one. So the outermost parts of the arc will be pointing towards their dip direction. And second, the steeper they are, the closer will they be to the equator, or they will be they will approach a straight line. And while the gentler they are, the more arcuate they become. Okay, right? So I think that's a decent review of your Cyrenet projection. Now, for kinematic analysis, actually, what we're gonna be using is not the arc plot or the arc representation. Actually, what we're gonna be using is the point or the pole plot. All right, now let's go back to the whiteboard. All right, now let's go back to the red discontinuity here, the 0.00045. Now let's try to give this a let me try to rectify this drawing. Okay, this actually should look something like this. Okay. Right now, let's try to imagine how would this look like if we're gonna plot it as a pole. A pole plot is basically imagine if this is your plane. You make another whiteboard. Can I make another whiteboard? Sorry. Anyway, let's just use this other space. If this is your plane, like this is the plane of your discontinuity, okay? The pole would be a line that is actually piercing this plane perpendicularly. Okay. Okay. And whenever this pole intersects the stereographic net, that would be the plot point of your pole. Okay. Therefore, basically, a pole plot is just a sort of a perpendicular piercing point representative of your discontinuity. Okay. So if this is the plane of your discontinuity, you basically have to pierce this with a perpendicular line or a pole and just allow it to pierce through the stereographic net or your bowl of noodles you make. And wherever it hits the bottom of your stereographic net, that would be the plot of your pole. Okay. Now, if we're gonna represent this one, so therefore it's gonna be plotting somewhere here. Okay. This would be the pole plot of this red discontinuity. Okay. So you can imagine that, okay, so it would be plotting somewhere here. Now, if you're gonna do the same for the other discontinuity, let's say the 00020 plane, the pole would look like something like this. It would be a bit more erect, it would be a bit more closer to the vertical. Okay. And it would pierce the stereographic net somewhere here. So the pole should, for this discontinuity, should look like this. Okay. So what can you notice here in terms of the locations of the poles relative to their arcs? Notice that the gently dipping discontinuities actually have poles that are actually closer to the center of the circle. Okay. So in a sense, it the poles are going like the opposite way. Okay. So they basically go the opposite azimuth. So you can see here this the pole for this plane is actually on the other side. It's basically just this is basically just a 180-degree azimuth. You're just flipping the azimuth by 180 degrees. So you're basically flipping the azimuth by 180 degrees, and second, you're also just flipping the dip angle by 90 degrees. Okay. So you basically just have to for the dip, you just basically have to subtract the dip of the arc from 90 degrees to get the tip of the pole and the steering net. Okay. All right. So I know this is sort of confusing, but I'm just I'm just skimming the topics for you to be ready for using the software. I think it's the DIPS software. Anyway, once you start dealing with the discontinuities in this exercise, you won't have to plot them manually. You'll be using the software. So I'm just teaching the basics again so that you can actually check your own work. Okay, so you have the capability to check your own work as you're working with the exercise. Okay. Right, so that's how the pole plot works. Okay. Now, I think we should start talking about contours. This is We'll be discussing this one. Create circles. All right, kinematic analysis. Okay. Just show you a PowerPoint for kinematic analysis. Okay. Can you see this PowerPoint presentation? I think it's working.
Yes po, sir.
All right. Thank you. All right. Yeah, this lecture is supposedly for the Bangsamoro Autonomous Region in Muslim Mindanao. So for information, we actually have two governments now in the Philippines. One is basically the national government, and you also have the BARM government. So they have their own government, they have their own DPWH, they have their own DOH, they have their own MGB. I'm not gonna comment. But anyway, this is supposedly one of our part of our work in DPWH, where we were supposed to provide training to the DPWH counterpart of the BARM government. Hmm. Unfortunately, that this did not push through for unknown reasons. All right, so this is just a chart. It's intended to show where are we in the big picture of doing rock slope stability analysis. Okay? I think it would be neat to emphasize this is where we are. We're doing kinematic analysis. If you're gonna go forward, you will eventually have to do some rock slope stability analysis or modeling. And before you can actually determine the strength of the rock, you will have to use the Barton-Bandis criterion. And once you determine the factor of safety of the slope, um, if it's unacceptable, you will have to do some mitigation measures and model and input that in the stability model until you get an acceptable factor of safety. Once you have fully stabilized the slope in your model, then you can say that you have properly designed your rock slope. Okay. Now, if you go back, kinematic analysis, you do it when you are dealing with a rock slope. Okay. And how do you know if you're dealing with a rock slope? Your rock has to be slightly weathered. Okay. There are also certain cases where your moderately weathered rock can also undergo rock slope failures. Okay. And in that case, you also have to do this whole set of analysis. Okay. Now, if your outcrop or rock material is heavily weathered, it will act essentially as a soil slope. So you have to use your soil mechanics strengths like the GSI, the Hope-Brown criterion, and analyze it as a soil. Okay? And you will notice here that a rock that is moderately weathered is actually very, very tricky to handle because a moderately weathered rock can actually undergo failure as a rock slope or as a soil slope. Therefore, if you have a moderately weathered rock, you have to do both analysis, okay? And see which kind of failure would be actually more likely to happen. Okay? All right. I think I can proceed. All right. Discontinuities. I've already discussed that. Kinematic analysis. Right. And this is basically about the analysis of orientations of the discontinuities relative to the subface. Okay, planar slides are formed by a single discontinuity plane. And then for the wedge, you need two discontinuity planes. Okay. And I think I just want to emphasize in this slide that the criteria for planar slide and wedge slides are essentially the same. Okay. They basically have the same criteria. The criteria is essentially the same, except for that the wedge slides you're applying the criteria on the intersection. Okay. For you to imagine this, if this is your planar failure, and this is your sliding plane. So for the planar failure, you're only dealing with one plane, this whole plane. For the wedge failure, you essentially you don't have a plane in the wedge failure, but you have intersection. Okay? And in this intersection is actually a line. Okay? And a line can be represented in the steer net as a point, and that point can still be represented again as a pole. Okay? So essentially, you have basically the same criteria. The only step that you have to do when you're doing wedge slide analysis is you just have to resolve. So you need to resolve the azimuth and dip of the intersection. Okay. So how do you do that? What you do is you use stereo net. Okay. So you can do that in the DIPS software, I think. I think DIPS software already automatically calculates that. Or you can just do it by paper, okay, like what you did in the structural geology. Right? And the criteria for both, let's proceed to the criteria for the planar and wedge failures. You have three criterion. First criterion is that their orientation should be more or less parallel to the orientation of the rock slope face. Second one is that the dip angle has to be steep enough to overcome the friction between the rock particles. And at the same time, it has to be flat enough to be able to exit the slope face. Okay? Therefore, this is sort of a Goldilocks situation where the discontinuity has to be just steep enough and gentle enough. It has to be steep enough to overcome the friction, but it has to be not too steep. No, otherwise it won't be able to exit the slope face. I'm gonna elaborate that in the next slides. And picture. Ito, this is a good one. Okay, criteria one. This is an illustration of criteria one. You can see here that the slope face is actually, this is the road. You can see the road here. And the slope is actually directed somewhere in this direction. This is the direction of the slope face. On the other hand, the direction of the discontinuity or the rock of the discontinuities, these bedding planes are directed somewhat parallel but slightly deviating from the slope face. Okay. But so we can see here that the bedding planes are dipping slightly away from the slope face, but more or less they're still more or less parallel. And you can see here you've had some recent rock planar failures here. Okay, so in this case, the slope face and the discontinuities are still more or less quite parallel to each other. Now, the second photo is an extreme example. You can see here, the slope face is actually oriented towards this direction, while the bedding planes or the discontinuities here, you can see that they're actually oriented towards this direction. It's basically almost perpendicular. Okay. And you can see here that there's no way these blocks of rock can actually undergo failure, no, except for the some parts of it. I'm gonna go back to the exercise document. I just want to introduce a term or a jargon. Um, Sorry, I just have to draw. So I just wanted to introduce the concept of daylighting. Yes. All right, let's draw an two rock slopes. Let's say you have two rock slopes that are essentially identical. Sorry. So they're more or less identical. And then you have two discontinuities that are different. So this is the side view. In case you're wondering, this is the side view of the two rock slopes. All right, let's say in the first rock slope, you have a discontinuity that is dipping moderately steep. Okay. And then you have another, and then in the other one, you have a discontinuity that is actually very steep. Okay. Now, you will notice that in the first case, you can see that the discontinuity is actually exiting into the surface. Okay. While the other one is just gonna probably head straight into the underground or the subsurface. Okay. Now, in terms of kinematics or in terms of possible movements, it's quite obvious that this block can actually undergo failure. It can actually exit this slope through this discontinuity. For this other case, there is no way this block of rock can actually go anywhere. It's not going anywhere. There is no kinematically possible movement for this block of rock. Okay. So this is what we call the lighting. Okay. This is the term coined by miners. Basically, their logic here for the name is that if the discontinuity is actually exiting or seeing some light in the surface, therefore, it's possible that this discontinuity can actually cause some rock slope failure. Okay, and that brings us back to the second criteria. The second criteria, which is the sorry, no, actually that's the third criteria. So this daylighting is actually the concept relevant for the third criteria, wherein the discontinuity dip direction should be flatter than the rock's slope face inclination. Okay, so that's basically the rationale behind this. Okay, so the bottom line here is that the discontinuity has to be less steep compared to the slope face inclination. Like in this illustration, sorry, it's already gone. Okay. And then criteria 2, basically the discontinuity dip inclination should be steeper than the friction angle. So again, I'm just gonna draw this for the sake of clarity. If this is your if this is your rock slope, and this is your discontinuity, okay? And let's say the friction angle of your rock, so you have this discontinuity, and it's actually this discontinuity is actually trying to cause some failure. Okay, this is actually trying to cause some failure by making the slope move, uh making the block of rock move out of the slope. Now, if you're gonna go back to your physics lectures or physics lessons, you will remember that you always have friction. You will always have friction existing through any surfaces that are sort of rubbing with each other. So you also actually have friction here, and they're actually resisting the movement of your rock blocks. Okay? And this friction will come from the roughness of your discontinuity and other interlocking parts of your uh, rock material. So if this okay, so if the angle of this discontinuity is around 20 degrees, and the angle of your friction angle is like 30, this is the most common, um, it's gonna be apparent that your friction, your frictional force will be greater than the shear forces existing within this discontinuity. So the friction angle can actually be sufficient enough to stabilize this block of rock. Okay, so there will be no failure. Okay. Now let's say you have a much steeper discontinuity. Okay. And its angle is, let's say, for example, 40 degrees. Okay. This will have a definitely much bigger shear forces, and it might be able to overcome the frictional forces exerted uh, by the rock, right? Okay, let's go back to the exercise document. Now, how do we plot or how do we represent these criteria into the steering? Um, okay, all right, let's discuss this one, this figure. If this is the plot, this is the arc plot of your slope face. Okay, this red line. No, sorry, I think it should be brown. So let's color this one brown. This is the slope face direction. So criteria one is about the orientation. Okay, if you'll remember, the orientation of the discontinuity should be more or less parallel to this face. Okay, so try to disregard the other symbols for now and just focus on my drawings. So the direction of this slope face is towards this direction. No? This is like east. No? It's the azimuth is directed towards east. Therefore, if you're gonna apply the criteria one, the discontinuity azimuth should be more or less plus minus 20 degrees relative to the azimuth of the slope face. So if we're gonna represent the criteria one, let's pick color yellow for example. It would be like this. Okay. So it means all the planes, all the arcs whose tangents are inside this zone are actually eligible for planar failure. Okay. Now we have a problem. Okay. Our problem here is that we actually want to use the pole plot for the stereo for analyzing for planar failure. So that's the standard. So this yellow line is actually the limits for arc plots. Okay. So if you remember earlier, if we want to convert an arc plot into a pole plot, we basically have to do a 180-degree flip and subtract 90 degree, subtract the dip angle from 90 degrees. So in this case, we're only concerned with the azimuth. So this is pretty straightforward. We simply have to flip this yellow zone into the other side of the steering net. So it will look like this. It will look like this line. Okay. So within this zone, all the pole plots that reside in this zone will be eligible for planar failure. Okay. Zone eligible. Okay, so this is the zone. This is criteria one. Wait. So again, all the pole plots of discontinuities that fall within this zone are automatically eligible for planar failure as per criteria one. By extension, all the pole plots of intersections are also eligible for wedge failure. Okay, so you can also apply this criteria for the wedge failure as long as you're plotting the intersections of discontinuities. And you can automatically do that in rock science dips, which will be done in your exercise. Okay, so this is just criteria one. We will be further shrinking this zone once we apply the other criteria or criterion. So for now, let me delete this shade. Okay, so this is your zone 1 and delete this yellow zone. Now, the second criteria is that the discontinuities should be actually be greater than the friction angle. Okay? They should be steeper than the friction angle. So normally, the friction angle that we use is somewhere between 25 to 35. For the simplicity of discussions, let's use 30 degrees for now. So let me use color green. So again, if you're gonna express this one, so if you're gonna express criteria 2 in the arc plot, it's quite simple. No? You only need so the criteria is that the angle has to be greater than 30 degrees. Okay? So it means that angles that are between 0 to 30 are not eligible for planar failure as per criteria 2. So we know if we're gonna start with the arc plot form of this criteria, we know that the edge of the net is actually equal to 0 degrees. Okay? If you go to the middle zone, this is your 45 degrees. And somewhere here is your 30 degrees. Okay? Oh, okay, somewhere here is, I think, 1/3. This is probably your 30 degrees zone. Okay? Okay, so this zone is between 0 to 30 degrees. Actually, it's quite, let me redraw that. So I'm just gonna draw again the zone for criteria 2 in terms of the arc plot. So this zone that I'm drawing, this is 30 degrees. No? So this is 30 degrees. So all the discontinuity dip angles that are greater than 30 degrees, okay, that would be your zone for criteria 2. Okay. So if we're drawing the if we're just drawing the criteria in terms of arc plots, okay, this is what would criteria 2 look like. Now we have to express this in terms of poles. Okay. So basically you have to take the opposite direction of this zone and get the complementary angles for this whole zone. Okay. So basically, I'm not gonna explain how that would be converted. You can do that by yourself in the rock soap dips. But basically, your zone would be would involve angles between 30 to 90. So so in the pole plot, so in the pole plot, actually this is your So in the pole plot, this is your 90, this is your 90, and this is your 0. So how would that look like? It would be somewhere between 30 and 90. So this is 90, this is like 60, this is 30 in the pole plot. Sorry, may check lang ako. Next. Okay. That makes sense now. So this figure is not really complete. I think this figure would be much more representative, no, of our what we're trying to do here. So I'm just gonna annotate again the criteria for planar poles. So this is your for your so this is your limit, no? This is your limit zone for orientation. Okay. So this is criteria one. Okay. And then so this is for the orientation or your criteria one. Sorry, nawala ulit. Or the azimuth. Azimuth. Now, for again, going back for the friction angle criteria, if you're gonna draw the friction angles that are eligible, that these angles are basically between 90 to between 90 to 30. Okay, so the zone would look like something like this if you are talking about the arc. Now, if you have to convert that zone into a pole, okay, it would look something like this. Um, so essentially, all angles that are between 90 to between 90 to 30. No? So parang ganito siya. Parang ganyan yung zone niya actually. Okay? Okay, so ganyan yung zone niya. Pero, so notice na meron na tayong parang overlapping. We have some overlapping zones here. Okay, so we have some overlapping zones here. And actually what only matters here are the zones that are actually intersecting. No? The purpose of the criteria is to narrow down the discontinuities that are eligible for planar or wedge failures. So for now, this is your intersection, no? So this is essentially the joint this is the combined criteria 1 and criteria 2 zone. Okay. For now, I'm gonna remove that. So now the last criteria is about the slope face, no? The joint in criteria 3, the joint has to be more gentle compared to the slope face. And let's say that the slope face is okay, let's say the slope face is 80 degrees. Okay. So let's try to draw that in terms of arc plot. This is your slope face plotted as an arc. And as per criteria 3, basically all the discontinuities that are more gentle compared to this slope face would be eligible. Therefore, if we're going to draw a zone that encompasses that criteria, this zone will represent all the angles between 80 degrees to 0. Oh, sorry, like 0 to 80 degrees. Okay. So these are all the eligible discontinuity angles. So if we're going to translate that into a pole plot, it would look something like this. 80. Okay, it would look like something like this bean shape. Okay. So now if we like okay. So the final zone that is eligible for planar failure or wedge failure would be this whole zone here. Okay, this small this zone that is acting as the intersection between all these three zones. Okay. Hence, all the pole plots that fall on all the discontinuities and pole plots falling under this zone would be kinematically admissible to planar failure. And at the same time, all the joint or discontinuity intersections that are falling under this one would be eligible for wedge failure. Okay. Okay, so that's how the kinematic analysis for wedge and planar failure works. Now let's talk about the toppling failures. Again, I have another PowerPoint for that. It's a very brief PowerPoint. Okay. Actually, sorry, hindi ko pa na-edit. If we're gonna go back to the document, I mentioned earlier that the important feature of a toppling failure is that you have a Roxo phase that is going opposite. You have a Roxo phase that is going opposite of the discontinuities. They have to be of the opposing directions. Okay. So if you're gonna go back to the PowerPoint, essentially you have two conditions here for the orientation. First is that the direction should be opposite of the Roxo phase, and you have a tolerance of plus minus 20 degrees. Okay. So eligible azimuths gamma d are equal to 180 minus the azimuth of the discontinuity plus minus 20 degrees. Okay. So this 180 degrees, this is just a number that is used to flip the direction of the azimuth, to flip the azimuth of any orientation. No? So you can either add or subtract 180. It doesn't matter. It's gonna flip the orientation in any way. Okay. And then you have this tolerance of plus minus 20 degrees. Okay, just like in the planar and the wedge failures. And then the second criteria is, this is what we call the interlayer slip test. This is quite lengthy to explain, but basically, when you're having a toppling failure, um, when you're having a toppling failure, if this is the slope direction, and these are your toppling blocks, as they are actually undergoing some toppling, there's still some friction that's existing between these toppling blocks. Okay, and that's what we call interlayer friction, or in our case, we want some interlayer slip to happen. Okay, so for that to happen, you have to be able to overcome the interlayer friction between the blocks. Okay. Okay, as per this text, no, the depth of the plates must be steep enough for interlayer slip to occur. If the face of the layers have a friction angle theta, theta j, then the slip will only occur if the direction of the applied compressive stresses is at an angle greater than the theta j with the normal to the layers. The direction of the major principal stresses is parallel to slope face dip angle gamma f. So the interlayer slip and toppling failure will occur on the planes with the dip gamma p when the following conditions are met. 90 degrees minus gamma f plus theta j is less than gamma p. So how do we interpret that? So I just simplified how you read this equation. In essence, this gamma p is your discontinuity dip, and it has to be larger than this number on the left side for the interlayer slip to occur. And what determines this left side? The slope dip and the friction angle. And note, the bigger the friction angle of your, or the smaller the friction angle of your rock, this number will be small. This number will be bigger. So the gentler the friction angle, the more likely that interlayer slip will occur. Okay? And that's intuitive, no? It's just common sense. You have two layers that are rubbing each other. So the smaller the friction angle, the less frictional force you have, and the more likely that they will undergo toppling. And the same way, the slope dip also influences this interlayer slip test. The bigger, sorry, I think there's a misalignment. It should look like this. So the bigger the slope dip, the theta j, the bigger the slope dip, or the steeper the slope dip, there's a bigger chance that you will also get interlayer slip. Okay, so again, that's intuitive. The steeper the slope, there's a bigger chance that, or basically you have less supporting pressures in this side, so it can actually topple. There's a bigger chance that these toppling blocks will undergo toppling because you don't have support in this side when you have a very steep slope. Okay, so how do we express that in terms of the stereo net? Okay. So let's go through this one by one. This brown line is your slope face in the plane plot format. Okay. So this is your 18 degrees. Okay. And then so normally, so if you will remember in the planar, and so if we're going to talk about the first criteria again, the orientation criteria, if you will remember in the planar in the wedge failure, the plane criteria is in here in this side. And then the pole plot criteria is on this side. Okay. But now, since we're talking about toppling, we have to flip things again. You have to do another flip here. So if you remember in the toppling, the slope face has to be opposite of the discontinuity or azimuth. So therefore, if you're gonna show how, if you're going to draw criteria 1 for toppling failure, this would be your zone for criteria 1. Okay. So this zone is the zone that is opposite direction of your slope face plus minus 20 degrees. Okay. For the arc format. So if you're gonna express this in the pole plot format, you have to flip this again. Okay, so marami kang flip na gagawin. You have to flip this again and it will look like this. Okay? . Okay. So it's quite confusing, but yeah, you're basically flipping it once to use to apply the criteria one, which actually wants the discontinuity azimuth to be opposite of the rock slope face. And then you're flipping it again to apply to convert from arc plot into a pole plot. Okay. So that's criteria one, and then criteria two is basically just the friction and it's the interlayer slip test. Okay. So I'm not gonna expound how this was determined, but basically the interlayer slip test is gonna fall under this zone. Okay. So basically this would be your whole rock toppling zone for pole plot format. Okay. So you can also reproduce this one once you start working with the rock science tips. Okay. All right. So so far do you have questions? Okay, so I assume you don't have any more questions. Uh, so for the exercise, I think not sure if I've already provided the exercise files, but the exercise brief or the exercise document contains all the stuff or the steps that you have to follow in order for you to produce the exercise output. No? So basically, it's a tutorial. It's basically just a tutorial for rock science dips. But I just had to introduce you the general concepts and method behind the kinematic analysis so that you can actually appreciate the stuff that you're gonna do in the exercise. All right, so I think I'm just gonna upload the exercise documents probably within the week. Okay, so just give me a reminder if I forgot or in case I forget about it. But anyway, yeah, thank you for attending. Okay, this ends the tutorial session for exercise on kinematic analysis. Okay. Yes, have a good evening for everyone and goodbye.
Thank you po, sir.
Okay.
Thank you,
Thank
sir.
you po, sir. Welcome.